Good morning. We're going to go ahead and get started. We'll give folks who are still working on the quiz another minute or two to finish up. But if you've already finished, you can open to page 22 in the packet. And while we're doing that, we'll just take a quick look at the calendar. So today is class number 5. We're just wrapping up our very first quiz. I think we have about 9 or 10 of them. I do drop the lowest quiz grade at the end of the semester. Today we cover section 2.3, which is the derivative function. And on the coming Monday, what's happening? Project number 1 is due. I just want to be clear, and I should have mentioned this at the outset with project number 1. On all projects, you are welcome and encouraged to talk to your neighbors, talk to the people in this section, talk to the people in the other section, talk to your friends, your family, random people on the internet, like talk to whoever you want to. But just all I ask is that you credit your sources, okay? Just say, I worked with so-and-so. That's all we need to see, all right? But I think working together with people on the projects does everybody some good. Okay, so let's go ahead and take a look in the middle of page 22. And we are on number 1. Can we go to Richard for number 1? Okay, let's pause right there. Last class, you guys did this mantra chanting thing. It actually was kind of weird from my perspective to see you doing it, but what is the derivative? Slope of, that was not mantra enough. What is the derivative?
The
slope of the tangent line. It is a number. It is the slope of a tangent line. That crazy looking formula is just the slope of a tangent line. Go ahead, Richard. All set. Okay, so what we're doing is we're going from the derivative at a particular point and saying, okay, that's just the slope of a tangent line at that particular point, to thinking of the derivative as a function. There is a tangent line at every point on this curve, yes? Every point on this curve has some tangent line. So every point on this curve, every x value on this curve has a slope associated with it. For this particular x value, it's about 4. And what's the slope? About negative 0.6. So I could think of the derivative as being a function. The input for this derivative function is 4, and the output is 0.6. So we could plot a point, couldn't we? You go over to 4, which is right here, and you go up to 0.6. Maybe right around there. That's a point, yes? And then I could take this thing and I can move it. Let's move it over here to, say, around negative, or we'll say around 3. At 3, what's the slope of the tangent line? It's basically negative 1. Don't say. All right. But yes. So for our derivative function, what's the input for this guy? It's 3. What's the output? Negative 1. And I'm plotting another point. I had another point. I had a point right there. And now I have a point at 3, comma, negative 1, which is right down there. Oh, lots of stuff. Right there. Yes? And you could imagine at every single point on the sine curve, every single x coordinate, there is some corresponding tangent line which has a slope which you can plot as the y value. And that's the leap for today, is we're going from the derivative at a particular number is a particular number to, okay, we could think of the derivative as a function. Any x has a derivative, has a slope, and we could plot that thing. And so we're going to see a bunch of that today. Okay, let's go to number 2. Abby? Okay, not a big change from what we did yesterday or last class to what we're doing today. It used to be a was a specific number. Now it's x, a general number, but it's the same formula. Abby, go ahead. Okay, thank you. Josiah, number 2. Oh, I'm sorry, we have another person at that table. Andy, number 2. Okay, let's give it a shot. So what we're going to do first is grab some easy points. And the points that I think are easiest are the extreme points. So I see 3 turning points, right? On the first day, and you might not remember this, we'll define it again soon enough, we called them critical points. That was in the very first day's class. These turning points right here are called critical points. And now that I think about it, actually, we skipped the example where we define them as critical points on the first day. But if you look on the first day's notes, I typed it, I swear, it says critical points for these turning points. And so what I want to do is I want to draw tangent lines. I'm just going to draw little tiny tangent lines. But these are special tangent lines at the turning points. What's special about those tangent lines? They're all horizontal. So these 3 things here have horizontal tangent lines. And what's the slope of all these horizontal lines? 0. So I'm just going to put right here, I'm going to put an ordered pair of numbers. Let's just ballpark. What is the x value for that bottom point? -1, comma, and then the slope. So maybe we'll put here, it's x, and then it's the slope. That's what we're plotting. What's the slope of that line? It is 0. So I've got a point -1, comma 0, which I'm going to plot right over there. That point is on my derivative function. And then we're going to ballpark this one. What's the x? 1.5, 1.4. What's the slope of that tangent line? Also 0. That's another point on our derivative function. It's going to start to take shape. Is the quiz in here? Okay, thanks. So we go to 1.4 and 0, somewhere around there. And then finally, what's the x at this point? 3. What's the slope of the tangent line? 0. That point is a little bit random. Oh wait, did I do a scale thing here? What's going on? 3. Oh yeah, 3, right there. 3, comma 0. So we can grab the zeros pretty easily because they have the flat tangent lines. Now we're just going to pick a few other representative points. I see this graph as being several different chunks. I'll do it here in the disappearing pen. I've got this chunk until the first point, this chunk to the second point, there's another chunk, and there's a fourth chunk. I see 4 chunks, right? Just sort of broken up by these 3 turning points. So I'm just going to pick a random point at each of these 4 chunks. I'll pick this one, and I'll pick that one, and maybe this one. You can pick any point you want. We're just trying to get a flavor for what the derivative function might look like. And so what we'll do is we'll, at each of these points, what are we supposed to draw? Supposed to draw the tangent line. So I'm going to draw my tangent line at each of these points. We're just ballpark, eyeballing it. Tangent line, tangent line, tangent line, tangent line. So you just make your best guess. And we've played that game before where you have a tangent line and you estimate the slope by literally counting boxes. I picked the red points because they were sort of in the different pieces of the curve separated by the purple points. So I had my purple points as the easy ones, and then I just picked one point in between every pair of purple ones, and then another one on each end. But you can pick any ones out there. Okay, ballpark, what's the slope of this first green tangent line? Maybe -6. If you say -3, if you say -10, there's a wide range of answers that are all acceptable. Just some fairly big negative number because that's pretty steep and it's downhill. And if you wanted to draw this line further, you could really count boxes. So let's start getting our point here. What's the x coordinate? Is -2, and then the slope we had said we'll just go -6, but again, it doesn't have to be exactly that number. And so you plot the point, -2, -6, -2, -6. We see how this works? And we're starting to kind of get a sense of the shape of the derivative over there. Okay, what's the x of this red point here? About 1/2. Slope of the tangent line, maybe 2. We'll take it. And so we'll plot 0.5, comma 2. And then I'll ask you guys to grab the last 2 red points, draw your tangent line as best you can, estimate the slope, and plot 2 more points on this graph to the right. Okay, so we'll grab these last 2. What's the x of this random red point over here? Looks like it's around 2. Tony says slope is -2. Is that close enough to numbers that you guys had written? So 2, -2. And then finally, the last red point, what's the x? Maybe 3.7. And then the slope, maybe about 2. Again, doesn't have to be exactly that. We go to 3.7, we go up to 2, and that's our last one. And so I now have 1, 2, 3, 4, 5, 6, 7 points that are on my derivative function. Did I miss something? Okay. Okay. And then we connect the dots in some reasonable fashion. Just draw some curvy thing that hits those 7 points, and you're going to have a pretty good sense of what the derivative function looks like. So it goes up, it hits, it comes down, it hits, it goes up, something like that. And I just want to highlight, all right, so first of all, I missed some of the points, but it's perfectly okay for your derivative function to go lower than the point that you plotted. We didn't necessarily grab the highest points or the lowest points on the derivative function. We just grabbed some kind of random points. So again, there's lots of range for acceptable answers to this question, but essentially I'm looking for something that goes up and then down and then up and hits those 3 spots on the x-axis. And how high it gets or how low it gets, we really don't know. We're just estimating. Questions on this one? Okay. We'll go to the next page, number 3, and we'll go to Josiah. Okay, so if you are flat, meaning horizontal tangent line, like those 3 turning points, then what was the value of the derivative? It was 0. Flat means the derivative is 0. Josiah, you can keep going. Okay, so let's take a look at the increasing parts on our original. So on the original thing, looks like we were increasing in here, between there and there, yes? And I just want to grab those 2 points. Maybe we'll highlight it so it'll stay up there. So from here to here, the original function was increasing. And I'm just going to grab that part of the curve on the derivative. So that was from -1 until where? Until about 1.4. Those were the two, that's the ends of our increasing part. So from -1 to 1.4. Okay, so -1 to 1.4 is that part. And if I look at the piece of the derivative that is above that yellow, then what's true about every one of those points? They're all positive. You see that? They're all above the x-axis. It's kind of surprising until you think about it. There's no reason they all had to be positive. Maybe it was just a fluke. Let's take a look at the other part that's increasing. We'll say from here and up to the top, that's increasing, right? So that goes from 3 and then to the right. Okay, let's take a look at 3 and then to the right. So 3 and then to the right is this part. And what do we see about that part of the derivative function? Positive. Maybe it's not a fluke. So if the original function's increasing, then the derivative is a positive number. I think that makes sense. If the function's increasing, then what kind of a tangent line do you have? Like an uphill one, a positive one. And if a function's decreasing, what kind of a tangent line do you have? Something negative. And so that's what's going to go in these next 2 blanks here. So first one, if f is increasing, then f prime is positive. And if f is decreasing, then f prime is negative. Fundamental facts about the derivative. Okay, number 4. Let's go to Todd. Sam? Okay, so I'm going to totally make up some physiological stuff because I don't know anything about it, but I'm going to assume that like if you're undergoing some significant surgery, then that might be taxing on your heart. And so it might be that they would want to monitor your heart rate even after the surgery was over to make sure it got back to normal. Like we all have a resting heart rate. And if we're running, then the heart rate goes up. And so maybe they just want to make sure that the heart rate is doing what it's supposed to be doing. And so here's something easy enough to count. They put a little, thing on your chest that just moves every time your heart beats, and then it's just got a counter. And so 40 minutes after surgery happened, your heart beat a total of 2,806 times. Okay? Easy enough to count with one of these gadgets that they have in the hospital. And so what I want to do is find the slope of the tangent line at 42. So you can imagine just plotting these points. I'm not going to draw them, but you could plot all those points, and you'll just have, 5 dots. And the slope of the tangent line, okay, first of all, is the function going to be constant, increasing, or decreasing? Hopefully increasing, yes? But if it's constant, then you have flatlined, like literally, like flatlined, right? And if it's negative, then you had negative heartbeats. That doesn't make sense. So hopefully it's increasing, and you can see that it is from the bottom row. But all we're going to do is just find a couple of secant lines. We have no hope of finding a tangent line for this. You have 5 points. You need infinitely many to find a tangent line. So we're just going to find some secant lines. The focus here is t equals 42. How about some of you guys find the secant line connecting 40 to 42? That would be like the left hand of the point you're interested in. And some of you find the secant line between 42 and 44. And then maybe we'll just average the 2 slopes that we get. So just do a slope calculation, pick either the purple or the red, and we'll get our 2 answers up here. What can you say? Okay, so first we'll interpret them after we average them. So we're just going to average these 2 numbers, and we're going to call that the slope of the tangent line. At least that's our best guess. So slope of the tangent line, which if I wanted to write it in terms of like derivative notation, I would write f prime of, think for a second, there's a number that goes in those parentheses. It's 42. It's the number that we are focusing our attention on. It's the input variable. It's t in this case. And according to our calculations over here, if we just average these guys, then that's going to be our best guess for the slope of the tangent line. All right, what do we get? That's 568.5. Double check me on that. Yes. Okay, so f prime of 42 is roughly 68.5. Now, in terms of interpreting any kind of like word problem like this, Lindsay, is that all right? Okay. In terms of interpreting, writing down the units of the number will take you very far in terms of figuring out what that number represents. So something that I'd written before, the units of the derivative are the y units over the x units. This is something worth knowing. The derivative for the units for the derivative are always the y units over the x units. What were the y units in this problem? It's heartbeats. X units, minutes. So the derivatives units, beats per minute. So our interpretation, can you guys write a sentence? Write some sentence about this patient interpreting this fact. Your sentence had better include the number 42 and 68.5. They both need to be in there. Okay, so something like that, doesn't have to be word for word, but 42 minutes after this person's surgery, the heart rate was about 68.5 beats per minute. Any questions on the sentence? All right. So that's that one. And I'll also say, so we've talked about the derivative, and we keep mentioning this word rate. Average rate for the secant line, instantaneous rate for the tangent line. And I just want us to start being aware of that word rate because it appears in everyday language. We aren't necessarily thinking of it as a derivative, but heart rate is a very natural phrase for us to use here, right? Nowhere in this problem did it say find the heart rate. But heart rate is a common phrase that we know, and that's the phrase that we would use for 68.5 beats per minute. So it's a rate, it's a derivative, and it's something that we've been doing kind of naturally for a while. All right, let's take a look at this function right here on number 5. Okay, so number 5, we are at Toby. Okay, So what I'd like you guys to do is pick, say, 3 points. Any 3 points on this curve, but space them out a little bit. Draw 3 little tangent lines, estimate 3 slopes, and then plot 3 points of the derivative. And you're just going to plot it on the same set of axes. And check with your neighbor if you're getting stuck someplace. Okay, so let's see how we're doing. I picked 3 points. They're probably different from the 3 points that you picked. I estimated 3 slopes of tangent lines. They're going to be different from what you estimated. But ultimately, when we draw the final sketch, when we try to connect these points in some reasonable fashion, we should get something that looks similar. And so I'm hoping that you guys get something that kind of looks like it's really, really close to the x-axis for most of the time. And I didn't pick a point between 0 and 1, but if I had, what kind of tangent lines do you have here in the beginning of this curve? They're actually really steep. So, I mean, okay, so I'm kind of like cheating in that I know what the answer is supposed to look like beforehand, but if you plot a few points in there that are near the origin, you're going to get really, really steep tangent lines. And pretty quick, they're actually going to be off the grid, way steeper than 3. Yeah, I mean, it kind of does look like an exponential decay thing. Okay, so anyway, we get something like that purple thing. Again, there's lots of range for error in terms of acceptable answers. Number 6 says use the limit definition of to find f prime of x. So let's try one of these here. First, we need to remind ourselves of what the limit definition is. So I'll put some of it and ask you guys to fill in other parts of it. See if you remember any piece for this limit definition of the derivative. The thing on the bottom is the easy part. What goes downstairs? H. All right. And that also has to do with the limit. What is the limit? As h approaches 0. Okay, so I think those are kind of easier to think about. Upstairs, it can get kind of jumbled up in our minds. Last class, it was f of a plus h. This class, it's now x plus h. Last class, it was f of a. This class, f of x. So that's our derivative definition. And if you write that thing down enough times, it will become more and more familiar to you. So I'd encourage you to just try to keep writing that without looking at some other reference. Okay, so we give it a shot. And this problem equals, limit as h goes to 0. I'm going to get lazy and stop writing that, but if you do that on my test or quiz, you're going to lose points. So this is where a do as I say in a moment instead of a do as I do. So limit as h goes to 0. Okay, let's do this piece first. F of x. What is f of x? It's the square root of x. It's given. We just copy that. So right over here, we've got this minus square root of x. Downstairs, still an h. The first thing, that's the tricky thing. F of x plus h. It means you are plugging in, instead of the x in the formula, you are putting x plus h. What is it? It's the square root of x plus h. If your h is on the outside, you're going nowhere in this problem. That h is inside of the function. It's part of the input. Okay, somehow we need to deal with this thing. You guys have seen a technique at some point in a previous math class for how you can take a fraction with radicals and make it look different. I'm not saying better, I'm just saying different. You could write stuff with negative exponents. We need a very specific technique for this one. Yeah, so we'll talk about the 1/2 if we need to. So unfortunately, squaring is not something we're allowed to do to a fraction. Like you can't square a fraction. It will usually change the value of the fraction, but it's a good guess because we want to get rid of those radicals. What if the radicals were in the bottom? What would you do to get rid of, like if you had a radical, if that stuff that was on top was on the bottom? Don't you have a technique to get rid of the radicals in the bottom? It's called rationalizing the denominator usually. And it's actually a technique Garrett had mentioned on some previous problem, and we didn't follow through with it on that one, but we are here. We need to multiply by the right thing. Do you guys know what the right thing is? It's the conjugate. It's exactly what's up there, except that subtraction becomes an addition. So we're going to multiply up here by square root of x plus h plus square root of x. Have we done stuff like that before? We may never have done it when the radicals were upstairs. But if the radicals were downstairs, this was the technique to move those radicals. But I can't go around just multiplying the top of a fraction by something without right away balancing the scale and multiplying the bottom by the same thing. Okay, so we're going to do the rest of this kind of quick, and if you want to see the details, I'll post the PDF at some point early this afternoon. But if you FOIL upstairs, square root of x plus h times square root of x plus h is just x plus h. All right, that's a good thing. I'm going to leave some space. Imagine that the limit as h goes to 0 is in that space, because that's what should be there. When we do the outers and the inners, you know what happens? They cancel. That's the point of multiplying by this thing called the conjugate. If you do the outers multiplied and the inners multiplied, and you add them together, we will get 0. So they cancel, and then we're just left with the lasts. Minus radical x times positive radical x is just minus x. Downstairs, you might be tempted to do what? Maybe multiply that h through. Don't. It's not wrong, but it's going in a direction that is further from what you want. So do not do anything on the bottom. Last class we had some complicated fractions. I said don't FOIL on the bottom. Now we have a radical down there. Don't distribute on the bottom. Really don't do anything on the bottom. The top is where the money is. Now something nice is about to happen. What is it? X's cancel. And once we cancel those x's, what's left on top? Just h. And that is wonderful to see, because what can we do with that h? We can cancel it. It's the h in the bottom that's been our nemesis this whole time. So you've got to find an h upstairs to cancel it. And we just did. So this is 1 over radical x plus h plus radical x. Okay, and now I'll write down the thing I should have been writing the whole time. We should have had this limit as h goes to 0 in the front of each of these. And then we actually just send h to 0. What do you get on the bottom? Square root of x plus nothing is just the square root of x, plus another square root of x. What is that equal to? It's not 1 over x. Yeah, it's plus. It's plus. So we got square root of x plus another square root of x is 2 square roots of x. Odd. Because we're sending h to 0 finally. Yeah, so you replace the h with nothing. Okay, so after all that work, I'll write down our big conclusion here, that if f of x is equal to, what did we start with, square root of x, then f prime of x, what did we figure out as the derivative of that function? 1 over 2 root x. Of what? Yes. And so I think Tony's making a connection here. Everybody have what we need here at the bottom? Because I want to look at the graph again. Okay. The function that we started with in the graph wasn't given to us as a rule. It was just a picture. But does that picture look like any sort of standard function that you might have seen a bunch of times? What does it look like? Yeah, the black curve that was originally given. I'll give you a hint. Look at number 6. Square root of x. If I asked you to draw the square root of x, can you picture something starting at the origin and then? Okay, in fact, that's what that function is. For example, what is the square root of 9? 3, which is the y value there. Okay, and then what we figured out using all this algebra is that the derivative is 1 over 2 radical x. Now, probably we don't have a good sense of what that thing looks like. I wouldn't say that's in our standard kind of toolkit. But, and you don't need to do this at this moment, but if we just threw a quick graph in here of 1 divided by the 2 square root of x, oops, 2 square root of x. And I think we should see, okay, not a whole lot. So how about we fix our window a little bit so that we're kind of looking closer, 0 to 5 on both. And I'm hoping that this thing looks quite similar to the derivative that I drew up there in purple. How did we do? Okay, let's go. Let's go to the next page, number 7. Where are we now, Bubba? Okay, so I'll just remind you what we figured out last time was that the derivative of that function, square root of x, is 1 over 2 square root of x. So if, for example, we wanted to find f prime of 9, all we do is plug 9 in for that x, yes? 1 over 2 square root of 9, 1 over 2 times 3, 1 over 6. Go ahead and find the other two derivatives, f prime of 1 and f prime of 4. What is f prime of 1? 1/2. What is f prime of 4? 1/4. And these are really, really precise points that we were attempting to plot before. Remember I had said we're plotting x and we're plotting the slope when we're trying to graph the derivative. So what was x for this first one? 1. What was the slope of the tangent line? It's the half. That's what the derivative is. So we should have plotted the point 1 comma 1/2. Now, we probably didn't plot exactly that point, but something close to it maybe. If we, I mean, some of us didn't pick 1, but hey, that's money right there. 1 comma 1/2. Now you might think that I was cheating and using that rule, and I wasn't, because look, 1/3 was my next guess, 1/5. But anyway, it should be something close to those numbers, right? The next point that we found here, what's going on there? Next point that we found was 4 comma 1/4, and then finally 9 comma 1/6. So those are 3 points that are exactly on the derivative. We should have found something near that by just estimating slopes of tangent lines. Okay, number 8 is going to be a real tease. Let's go to Tiffany. Okay, so here's a rule which some of you guys probably know if you've already seen calculus. In fact, this rule might be what you think calculus is. But does anybody happen to know this rule? What is it, Kevin? N times x to the n minus 1. That is something known as the power rule. For example, if we were thinking about f of x is x cubed, then this gives us a very, very fast way to find the derivative. It says you take that power, it's n in this one, and you bring it right down to the front. So what comes down to the front in this case? 3 times. Then you put an x, easy enough. The new power is 1 less than the old power. What's the new power? 2, 1 less than it was. The derivative of x cubed is 3x squared. And I'll tell you that was a whole lot faster than doing the limit definition like we did on the bottom of the previous page. Now I said it's a tease because we don't get to use it just yet. I'm bringing it in just for this one moment in time. I will say that once we get past the first test, on the very next class, I think I'm saying this true, Introduction to Derivative Formulas. It's the first class right after the first test. That is when we see the power rule, and from that moment on, we will never have to do this limit definition of the derivative again. Unfortunately for you, you haven't taken the first test yet. So we're just using it just as a little kind of sneak preview. But can you guys find the derivative of the square root of x? First thing you need to do is rewrite that as x to some power. Don't forget to use good notation. You're finding a derivative, give it a label. F prime of x equals. So what comes down in front? 1/2. Then we copy the x. Then we subtract 1 from the power and we get negative 1/2. So in theory, that's the derivative of the square root function. Now that doesn't look exactly like the derivative that we did all that work for on the previous page. So let's see if we can rewrite this. There's a 1/2. Now if you see a negative power, where is the thing really? It's really downstairs. So I'm going to put it downstairs. What's the power become if you put it downstairs? It becomes positive. So x to the negative 1/2 up there is the same as x to the 1/2 down there. Okay, so I guess it's a 1/. That's what negative exponents mean. And then if I wanted to mush those two fractions together, what's on top? 1. Downstairs, there's a 2. X to the 1/2 is also known as square root of x. And that should look familiar because that was what we sweated over on the previous page. We got 1/2 square root of x. Yeah, it was. All right, number 10, some calculator stuff. Who are we up to now, Lindsay? And then all that stuff. Okay, so let's see if we can get our calculators to look like that. So we go math, which is on the left-hand side. Then you can scroll down and you'll see the thing we're looking for is this thing called n-deriv, but it's math 8. It's always the 8th one. So you can either hit enter or 8. And what I'm looking for is the derivative of the square root function. So I'm going to type in the square root function. Second square root of x. Don't forget to close those parentheses, which the calculator automatically opened when I hit the square root button. And then the comma. A lot of people have trouble finding the comma. It's right above the 7. And then this is going to be kind of funny, but you have to tell it what the variable is. Now, for almost every problem we do, it's going to be x, but you still have to specify the variable is x. And another comma. And then what you have to do is tell it where you want to evaluate the derivative. Now, we did the derivative up at the top here at 3 different points. We found f prime of 1, 4, and 9. Let's do each of them, but one at a time. So if I just say 1, what did we say the derivative was? F prime of 1 was 1/2. If I hit enter right here, what do we get? Calculator's not as smart as we thought. It is estimating. The calculator knows zero calculus. It is just approximating slopes of secant lines, and it got pretty darn close to the right answer, which is 0.5 exactly. You know, like that is a tolerable error. It just makes a table. I don't even think it makes a table. I think it just picks a point that is just a tiny bit on this side and a tiny bit on that side, finds one secant line, and that's what it comes up with. Okay, if we wanted to do that again, hit second entry, and let's try to find the derivative at 4. Now we had said the answer was 1/4. How did it do? Did you guys get exactly the same as me or different? Okay, sometimes there's even little differences from one calculator to the next. And what were your answers like, Todd? And the answers, did you get exactly 0.5? Fancy. Okay, so that's how we find the derivative at a function. There's the syntax. You type the function, you always type x, and then you tell it what value is the independent variable. And it turns out we can actually get the calculator to give us this graph right here, the original and the derivative, without knowing what the formula is for the derivative. So here's how we do it. The directions are written out there, but we'll just do them up here together. So I'm going to go into y equals, and I'm going to type in my original function, square root of x. Now, for the purposes of graphing the derivative, I'm going to pretend I don't know the answer. We know it's 1/2 square root of x, but it's no fun typing that. I want to show you the calculator can give you the graph even if you don't know what the derivative is. So here's how we do it. You first find that n-deriv command again. So remember that was math and then 8. Make sure you're doing that under the y2 line. And what I'd like to do is type, well, I mean, I could just type the square root of x right here so that it looks exactly like it did up there, square root of x. Or you could go into vars and then y bars and then function and then y1. So either retype square root of x or do that if that's easy for you to find. The reason I like this is that if you decide after we do this to change the y1, then you'll get the right graph automatically in y2. Okay, what comes after the function? We go comma, and then we go x, and then we go comma. Now on the home screen, we had to type in a number. Find the derivative at 4. But here, you can tell the calculator to find the derivative everywhere by putting another x. And so I think I wrote that out. It's right here. So y1, comma x, comma x. And then I said what a good window is. We can try 0 to 10 and 0 to 3. And so if we have all that typed in, then we should get our square root function. And then we should get the derivative. Notice how much slower it graphs the derivative, right? It is doing substantial thinking to try to graph the derivative because it is literally plotting point by point. At every x value, it's drawing a secant line that's darn close to the tangent line, plotting that point, and then moving on to the next point. So that's why it's a lot slower. Fancy, but it was slow. So if you missed any of those commands, check out the YouTube video. I can walk around if anybody got stuck there in any of the commands. All right, 5 minutes is not near enough time to do this, but you can start this. So turn to the next page and see how far you guys can get. Directions are at the top.